An atom is, what is an atom? Do you guys know what an atom is?
Smallest structure of a cell.
Smallest structure of a cell.
It is the smallest unit of any substance.
Smallest unit of any substance, okay? It is the smallest part of matter. It is storage of molecules. No, Satvika, it is what molecules are made up of, okay? Pure substance, smallest part of an element. All right, very good. So, yes. So, atom is the smallest part of matter. And so, basically anything, like this pen that I'm holding in my hand, it's made out of plastic. So, plastic is made out of carbon and hydrogen atoms. So, basically, the tiniest particle possible in existence is called an atom, okay? Now, what is an atom made up of, and how did scientists come about discovering all of these things that the atom is made up of, okay? So, to give you an example, let me see if you guys can spot the atom on the picture on the left hand side in the slide. So in the slide, there's a picture on the left hand side. Tell me if you guys are able to spot where the atom is here. So if I zoom into this area and I look at that tiny little dot, and that is called as, that is the picture of an atom, and that atom is the strontium atom, which is illuminated by blue-violet laser light. Now, how this picture was taken is that you have, like a camera was set up, and that camera was made to take 1,000 pictures one after another continuously, okay, while this laser light was illuminating this atom, okay. So when this camera took 1,000 pictures, all of these 1,000 pictures were, put on top of each other, and that is when, the camera is able to see that light, the dot of a light, okay, and then we are able to tell, okay, that is a strontium atom. But with the naked eye, we cannot see the atom, okay. So an atom is about the size of a millionth of a millimeter. So if you take a ruler, right, in the ruler you have, centimeters, and then inside the centimeters you'll have 10 millimeters on your scale. So if you look at that 1 millimeter, which is so tiny, divide that into 100,000 parts. That is how small an atom is. So with all of the current technology, with all of the cameras, with the laser light and all of this technology, we are finally able to see that that is an atom. And we cannot even see electrons, neutrons and protons. So we can't even see the subatomic particles. So how did the scientists back so many centuries ago, when they did not even have they did not even have all of this technology, were able to tell that there are protons, neutrons and electrons? Well, actually not too many centuries ago, a few decades ago, okay? So, all right, so cathode rays and electrons, we had discussed this in the previous classes. So basically what cathode rays are, nothing but electrons, okay? So if you guys are not sure what electrons are, let me just tell you that an atom consists of a nucleus. Inside the nucleus, I have protons and neutrons. Okay, so inside the nucleus, I have protons, which are positively charged, and neutrons. Inside the nucleus, I have protons, which are positively charged, and neutrons, which do not have any charge. And around the nucleus, there are electrons revolving, and these electrons are negatively charged, okay? The atomic models, okay? So J.J. Thompson was the first one to discover electrons. So what he visualized, or what he imagined, was all of these electrons are kind of like how seeds are inside a watermelon, okay? So I have seeds inside the watermelon and how they're spread out. So similarly, electrons are also basically those seeds, and the pulp, which is the red part of the watermelon, that is the positively charged substance. Okay, that was the model proposed by J.J. Thompson, and he was the one who first discovered electrons. How did he discover electrons? He did the cathode ray experiment, which I just skipped just now, right? So he did that experiment. Yeah, so the next atomic model is the Rutherford nuclear, planetary, solar model. They are all the same name, they are all the same model but with different names. Okay, so if somebody asks you what the nuclear, planetary or solar model is, it's basically the Rutherford's model. Rutherford was a scientist, and let's see what he did. Okay, so he performed this thing or this experiment called the alpha ray scattering experiment. And basically what he did, he put a radioactive substance inside this block of lead. So this is a block of lead, and he put some radioactive substance inside this. Now, can you tell me why did he have to use this block of lead? He could have simply just kept the radioactive substance, right? What is the purpose of this lead block?
So that it can block its radiations.
Okay, why does it have to block the radiation?
Ma'am, they are very harmful rays.
Very good, yes. So the radiations are really, really harmful to us. So in order to protect themselves, they had to shield the radioactive substance, okay? Yes, Ridyansh?
Ma'am, actually, radiation, if like, it can also be helpful. For example, cancer cures. But only different types of radiation are like harmful. There's alpha particles, which are essentially helium atoms that don't have any electrons. There is beta, which are electrons with the specific properties, and gamma is just electromagnetic radiation.
Okay. You're going too much into detail. That was not my question. My question was, what is the purpose of just the block? So now we were talking about Rutherford's atomic model. So when what he did, he put radioactive element inside the block, and yes, polonium is an example of a radioactive element. Good. So he put radioactive element inside the block, and there is a hole inside this block. So the radioactive element will emit alpha particles. Okay, so it will emit a beam of alpha particles, and this beam is made to hit a gold foil. Okay, when it hits the gold foil, we notice that this beam, most of it went straight through the gold foil. That is why this is thick, this is also thick, and these are very thin lines. If you notice these lines, they are very, very thin lines. So most of the alpha particles, they went straight through the gold foil. That is what he noticed. The rest of the alpha particles, few of them were, deviated, deflected here and there. And this is a screen. This screen is called the zinc sulphide screen. Okay. So the zinc sulphide screen, what happens when these alpha particles hit the the zinc sulphide screen? We notice that there are these scintillating effects, okay, on it. So what is the meaning of scintillating or scintillation?
Some places on the zinc sulphide screen will light up.
Yes, so basically lightening up, like kind of like twinkling. So, or yeah, scintillation is nothing but lighting up or twinkling or glowing. Yes, Divya. Yeah, so what happens is, so we notice that this takes place. So the main thing to notice here is that most of the alpha particles went straight through the gold foil. Okay, so a few other things to keep in mind, that in this particular experiment, radium was used, not polonium. However, polonium is also a radioactive element. We could have used polonium also, not an issue, but in this case, radium was used. And in front of the lead block, we used this thin gold foil. Okay, so 0.0004 millimeters thick gold foil. So all Alright, so the rays were passed through the gold foil and scintillations were observed on the zinc sulphide screen. So before we get into what the conclusions or the observations of this experiment was, let's see what an alpha particle is. Okay, so alpha particle is nothing but it's a positively charged particle having 2 units of positive charge and 4 units of mass. Okay, so if that makes no sense, no issues. Let's take a look. Basically, helium atom. Okay, so helium has an atomic number. So this symbol is the symbol of this is the symbol of atomic number. So helium has an atomic number 2. Okay, so if the atomic number is 2, how many protons does helium have? Very good, yes. So atomic number is equal to the number of protons. Okay, for those of you who don't know, so helium has 2 protons. So let me just draw the structure of helium. Okay, so helium has 2 protons. So I'm just going to say 2 positive charged inside the nucleus. And I have 2 positive charges inside the nucleus, and the number of neutrons inside the nucleus, how many neutrons are there in the helium atom? Very good. So there are 2 neutrons in the helium atom. Okay. So I'm just going to put that as well. So 2 neutrons in the helium atom. So I have 2 protons and 2 neutrons, and around the helium atom I have 2 electrons. Okay. So 2 electrons around the helium atom. Now electrons are negatively charged and I have 2 electrons. So I'm going to put -2 because electrons are negatively charged. 2 protons which are positively charged. So I'm going to put +2. Okay. So when I add these 2 numbers, I'm going to get 0. Okay. So a normal helium atom is, it has no charge. Okay, so basically its charge is 0. There is no charge. Okay, however, what happens if I take away these 2 electrons? I take off these 2 electrons. I remove those 2 electrons. Then what happens? This goes away. Okay, so I'm only left with +2. Okay, and no more electrons. So the charge on helium atom after I remove the 2 electrons becomes +2. Does this make sense to everybody? Because number of protons and neutrons is same. Okay, not true. Number of protons and neutrons is same most of the time, but not always. Okay, which is why we don't say atomic number is equal to the number of neutrons. No, atomic number is always equal to the number of protons, not neutrons, not electrons. Okay, because the number of neutrons can change, number of electrons can also change. The only thing that does not change is the number of protons. Okay, so the number of protons is equal to the atomic number. Okay, so if I remove 2 electrons from a helium atom, the helium will be left with 2 protons, and there is nothing to balance that positive charge. So basically, you will end up writing helium +2. Okay. So now helium has 2 positive charges. Now the other thing to note is that inside the nucleus, I have 2 protons and 2 neutrons. If I say these one proton is equal to 1 unit mass. Okay. So if I say 1 proton is equal to 1 unit mass, and I say mass of 1 proton is approximately equal to mass of 1 neutron, then what happens? I end up getting 4 units of mass inside the nucleus. Okay, so basically that is what the statement is saying. Alpha particle is a positively charged particle having 2 units of positive charge and 4 units of mass. Where are these 4 units of mass coming from? 2 from proton and 2 from neutrons. Yeah, so basically alpha particle is nothing but helium ion. Okay, it is helium +2 ion. That is what alpha particles are. So alpha particles are emitted by radioactive elements like radium and polonium. They can penetrate through matter to some extent. Now, let's go back to the observations and the conclusions of this experiment that we saw, the alpha ray scattering experiment. What did that tell us? So, first thing it told Rutherford is that the atom is hollow, okay? Which is why most of the alpha particles passed undeviated, okay? So, if the atoms were solid, then every alpha particle would hit that solid part and it would have changed its path. Now, for example, if we look at this animation on the right hand side, what is happening is I have a dome structure, okay? So basically a hemispherical structure, and on top of that hemispherical structure, I'm dropping a bunch of marbles, okay? So when I drop these marbles, what happens once they hit the dome structure? They all hit the structure and they spread out in different directions. They deflect in different directions because there is that solid dome structure is present there. Now, if most of the alpha particles are passing through without being deviated, that means what? That means the atom for the most part is hollow. Okay? So basically, if I draw an atom, for example, let me draw helium atom, okay? So helium atom, this is the nucleus, 2 protons, 2 neutrons, and then this, there are 2 electrons. So this whole thing is an atom, okay? So this whole thing is an atom, but most of this atom, if you notice, is just empty. There's nothing there. Except for this nucleus, which is very tiny, most of the atom is really empty. So similarly, when we look at the gold foil has lots of gold atoms, and these gold atoms are mostly empty. Okay, that is what Rutherford concluded. So he noticed that most of the alpha rays, they went straight through the gold foil. They did not move here and there, most of them. So he concluded that the atom is hollow. Okay. The next thing he concluded, or that he discovered, was the nucleus. He discovered the nucleus. He noticed that very few alpha particles, 1 in 20,000. So that's how little. So 1 out of every 20,000 alpha particles, only 1 was deflected back. Backward deflection is possible only when the alpha particle hits something hard, rigid, and dense. That means if I drop something over here, it is only possible for it to bounce back straight up only if there is something very hard over here. Okay, that is what it is saying. So that means if there is something hard, that means something has to be there, right? And that something was the discovery of nucleus. Okay. And the composition of nucleus. Now he discovered the nucleus, he also discovered that the atom is hollow. But he hasn't yet understood the composition of the nucleus, like what is inside the nucleus. So he noticed that some alpha particles were deflected sideways. Okay, so some of the alpha particles were deflected sideways. We noticed over here that alpha particles, most of them went straight, but very few of them were deflected sideways. So this sideways deflection is possible because of repulsion. Okay, what happens when I have 2 positive charges close to each other? Yes, so they repel each other. So positive charges when they are close by, or even negative charges when they are close by, they repel each other. Basically, like charges repel each other.